gentlemen, please stand by. Your webcast, 4 ways to improve Linux performance for multicolored devices, will begin in 5 minutes. Once again, please stand by. Your webcast will begin in 5 minutes.
Multi-core devices. I'm Dexter Johnson, and I'll be moderating this presentation. Before we start our presentation, I would like to mention a few housekeeping items. For those of you who want to know if this session will be archived, the answer is yes. It will be archived and will be available for review within about 24 hours and can be found on www.spectrum.ieee.org/webinar. Once the archived webinar is available, a notification email will be sent to all the registrants. Secondly, we encourage questions, and I hope we have time for several, which we'll take at the end of our presentation. As your questions occur, please type them in the box provided on your computer screen on the left-hand side and hit the Submit button. You don't have to wait until the end of the presentation to begin submitting questions. As you look over your screen, you should also see buttons that allow you to enlarge the slides if you so desire. About volume control. If you're listening to the audio portion of this event over your computer speakers and you need to adjust the volume, turn your attention to the speaker icon at the top left of the screen. You may also need to adjust the master volume of your computer system. At the bottom of the slide in front of you are a couple of additional suggestions that will improve your viewing experience, including a resource page with today's presentation. Now I would like to introduce our presenter for today, Michael Christopherson, Director of Product Marketing, CTO Office at ENEA. Mr. Christopherson has over 30 years of experience in software development for deeply embedded telecom or networking systems. He spent the first 8 years of his career in the defense industry in SIGINT and Comment Systems. That was followed by 8 years in the telecom market, working with such technologies as packet switching, SS7, SONET, fiber in the loop, and DSL. For the past 16 years, Mr. Christopherson worked in product management, marketing, and business development for leading industry RTOSs, embedded development tools, and middleware providers such as Microtech, Mentor Graphics, and now ENEA, for whom he has served since 1998. And with that, Michael, I would like to turn it over to you, if you'd like to begin.
Yes, thank you, Dexter. Good afternoon, good morning, whatever the time it is for you. Welcome to our presentation, 4 ways to improve Linux performance on multi-core devices. First, let me just tell you a little bit about ENEA. This is won't take so long. Where just to give you some background about where we come from. Founded in '68, we primarily focus in wireless infrastructure, macro, small cell, media gateways, and terminals in the wireless space, and also a variety of applications in military, auto, industrial, and so on and so forth. Over 250 million of the estimated 325 million LTE coverage is powered partly by ENEA solutions, and we run in more than 50% of the world's base stations. So we're a major player in the telecom communications infrastructure market. We've recently announced just this past year and are now on release 3.0 of our commercial Linux distribution powered by Yocto. So ENEA does provide a Linux distribution, and that Linux distribution will support most of the technologies that we're going to be talking about today. We have global presence in all major markets and continents, and we're headquartered in Stockholm, Sweden. So, on with the show. The agenda, as was described in the abstract, is we're going to be talking about 4 approaches to enhancement of standard Linux performance for embedded multi-core devices. And specifically, those are the preempt RT config patch set, the a technology called ENIA LWRT, Lightweight Runtime Environment, which is a lightweight threading model on Linux. We're also going to be talking about Open Event Machine and hypervisors or thin kernel solutions. And what I'm referring to there is various virtualization techniques that can help really accelerate and provide better real-time performance with Linux-based systems. And I'll explain what that actually means later. So we're going to do sort of a pros and cons analysis of each of these technologies for best fit in performance and other kinds of characteristics. And we do have some performance comparisons across these 4, not a complete set, but some. And we'll get to that as we get into the presentation. So, since the main topic here is performance, the first question we have to ask is, what does performance mean? I mean, there's many measures of it that are often referred to, and sometimes it gets confused when we're talking about performance. There's different kinds of performance. There's real-time responsiveness, in other words, latency. How quickly does a system respond to an external stimulus or event? And oftentimes it's very related, and in fact almost all the time it's related to deterministic response, meaning a hard time limit over which you cannot exceed in terms of response to an event. So that's one measure of performance. And throughput, of course, is another measure of performance. How many packets, data objects, or flows can you process per second? Now throughput is often quite independent of real-time responsiveness. It doesn't have to mean short or even deterministic real-time response. Sometimes you can have both throughput, high throughput or good throughput, and real-time responsiveness. And then there's a third area that we refer to in terms of performance, especially in the Linux world, and that's high-performance computing. And that's more like massive compute-intensive applications like modeling, weather modeling, very big simulations, and so on and so forth, requiring lots of mathematical-related computations. High-performance computing does not the same as throughput. And in fact, in today's presentation, we're going to be talking about real-time response and throughput as the measures by which we're going to analyze these various techniques for improving Linux performance. So it's about real-time response and throughput. Well, even then, what does real-time performance mean? Real-time systems means that they have operational deadlines for system response, meaning it has to respond in real time, and usually means some sort of deterministic, some level of determinism. There's 3 levels of determinism. Non-real-time systems don't have any deterministic response, no guaranteed response time. And it's often qualified by best effort and so on and so forth. And this is very reminiscent of high throughput systems that don't really care about responsiveness or latency with respect to processing an event, but it's mostly about throughput. Real-time responsiveness means deterministic response. It can be seconds, milliseconds, microseconds, not necessarily short times, but often the case that we're talking about fairly short times, especially in real-time systems. So real-time system classifications. There's hard, where missing a deadline means total failure or pretty significant system failure. Firm, where frequent misses of the deadline, the performance deadline, is tolerable, but quality of service degrades quickly, meaning if you start missing the deadlines more and more often, then the quality of service, whatever your system is doing, degrades very quickly and could become unusable if too much. Soft real-time means infrequent misses are tolerable and QoS degrades more slowly. So again, just to reiterate a theme that I mentioned in the previous slide, real-time performance often is contradictory to throughput, but not always, and so we're going to take a look. Very quickly, examples just to drive the point home. Examples of real-time systems, hard real-time applications, automotive anti-lock brakes, pacemakers, industrial process controllers, robot control. You have to have real-time a hard level of deterministic response. Throughput is not an issue. It's about responding to events. Firm real-time applications are often most characterized by telecom applications. And in NIA, because we're so experienced in telecom infrastructure, some examples are 3G, 4G base stations, radio network controllers, baseband processing, signaling, and modems, and so on and so forth, and blah, blah, blah. So throughput is often an issue in many of these kinds of applications. And then soft real-time applications are sort of, some examples are IP network control signaling, various kinds of networking servers, edge servers, or servers that sit on the edge for content provision, live video, audio systems on the edge, and so on, where throughput with good enough real-time response is the issue. So just some examples to sort of help qualify what we mean by real-time responsiveness and how it relates to throughput. So, the heart of the presentation, 4 ways for better performance in Linux. Well, the preempt RT patch set, which basically reworks the internals of Linux. Okay? And we'll talk about exactly what that means. Thin kernel or virtualization techniques, sometimes called hypervisors. Basically what this, for those of you familiar with hypervisor technology, this refers to what is commonly referred to as type 2 hypervisors, meaning where you're actually running a very thin version of some kind of real-time operating system engine. Could be an RTOS or some variant of that kind of theme, running that at the base level right above the hardware, virtualizing Linux on top of it, but then providing a class of service where that is not actually true Linux applications that can be used for real-time acceleration. So there are many instances of this, and we'll talk about that later in the presentation. The third is vertical partitioning, user mode runtime, and lightweight threading, where in user space we actually put some real-time behavior into Linux, real-time scheduling into Linux in user space, and vertically partition the Linux environment in a multi-core device between soft real-time Linux applications and harder real-time applications that would use this user mode runtime, or in ANIA's case, our technology called LWRT, Lightweight Runtime Environment. And then lastly, we have Event Machine, where we do partition Linux into 2 domains, but one is really, really not running Linux at all if you really want to truly use the model. Even though it's lurking underneath, no service of Linux is actually running, no interrupts are occurring. So in effect, it looks as if half of the, or part of the multi-core device is actually running a completely different, what we call event machine model, as opposed to the other piece of the system that's running pure standard Linux. So, first poll question. Dexter?
Yes, Michael, thank you. This is our first of 2 poll questions today, and this is the chance for you, our audience, to participate and give us some feedback on your issues. And here's our, when you do answer this, please just use your screen and choose one of the options and hit Submit Answer. Don't chat back your response. And so our first question is, are you using or considering using any of the performance enhancement approaches listed? And that's the preempt RT, virtualization, lightweight threading, event machine, or none. And see, we get some, we have a pretty big audience today, so I'd like to get everybody's response. If you just pick one of those, and we'll and hit submit answer, we should get a good result here. Okay, everybody is taking the time. I appreciate that. We're getting some... All right, I'm not going to hold this up anymore, Michael. I'm going to push out these latest results for you. There you go.
Mm-hmm. Well, this is actually something that this is very consistent with a lot of data that we have. We know that Preempt RT is being discussed a lot in the Linux community, but there's also some issues with Preempt RT. So 20% sounds like a good number. Virtualization actually seems a little high to me, but I think that's interesting. Lightweight threading, I think, is a relatively new concept. There haven't been a lot of good implementations around in the industry. Ours, we think, is one of the best, ENIA LWRT. So I would think that number would be small. An event machine is even newer, and it's just really sort of coming to the fore in the last couple of years. And then none, or what I would call undecided, represents a majority. So I think we've got a good audience here that could be looking at potential performance enhancements as we sort of analyze the differences between these various approaches here. So, interesting results. Very good. So, first of all, the config preempt RT patch set. What problem is preempt RT trying to solve? Well, basically, the Linux kernel was not designed for very deterministic response to interrupts in particular. Lots of kernel interrupts disable places or in a multi-core device, lots of spin locks, so that proper synchronization can be obtained between various cores so that you don't have collisions and you have data protection and so on and so forth. Lots of other kinds of things like RCUs, read, copy, update. Lots of periods in the scheduler that lock the scheduler and so on and so forth. So it's been shown that Linux does not do a real good job of real-time responsiveness. Linux does do a pretty good job in throughput, in the throughput-related performance metric, which is why it's being used so much in so many applications. But in the hard real-time domain, remember the three different kinds of, the three different kinds of real-time, hard and firm, Linux has shown itself to require some modification to achieve the desired level of performance. And that is, in fact, the preempt RT patch set. It's actually been around quite some time. It started in the early 2000s, so 10 plus years ago, and before even multi-core technology became widely deployed, really initially developed for unicore technologies. And many contributors, and in fact in recent years there's been a very intense effort to work on the preempt RT patch set. What it does is it replaces most kernel spin locks with, otherwise known as interrupt disable time, or periods when the scheduler cannot operate, with mutexes, with priority inheritance. Mutexes are mutual exclusion semaphores, so that critical data can be protected as users sync up with each other, so that they're not stepping on each other. So that's an improvement. That means that you're reducing the amount of time that the scheduler actually can be available to service interrupts. Moves most interrupt handling to kernel threads. In other words, just the preamble or the top part of the interrupt service is actually implemented in interrupt mode, and then the rest of the handling is spawned off into a kernel thread. Okay, so that actually frees up a lot of time in terms of responsiveness because it means that high priority interrupts now can get more access to the device, to the Linux controlled device. However, that means that drivers must be modified in order to utilize the preempt RT patch set. So there's a penalty you have to pay for that. It's actually a very complicated patch. It patches well over 500 locations in the kernel, and I think this is almost a year old now. 11,500 plus new lines of code in total. It's probably grown since then. I don't have the exact latest figures, but so it's a very complicated patch, and it has to be reinstalled for every inversion of Linux that you that you upgrade to. And it's system-wide in scope, meaning it doesn't just affect one or two cores, it affects all cores that are handling interrupts. It improves, though, the fundamental thing about the preempt RT patch set is that it improves real-time performance dramatically, and determinism, getting all the way down to firm real-time, satisfying firm real-time requirements, and perhaps, although not widely believed, perhaps some kinds of hard real-time performance requirements. But at least we're getting down into the firm real-time performance deterministic behavior that we talked about before, and that is sort of a hallmark of many communication systems or telecom systems. But it does this at the expense of throughput. Let's take a very simple example. Now this is just one benchmark. It's standard Linux net performance benchmark. Okay, and I won't bother to explain net perf to you all. You can look it up. But notice the takeaway from this is, look at the top in the pink or the red as you see it, standard Linux, and this is Linux 3.6.4. The throughput on the standard test measured at 8,782, what is it, megabits, no, I can't quite read it. It's too small for me to read in this diagram, and I can't quite remember what it is, but the number that you need to know is 8,782 versus when you employ the preempt RT patch set, it halves. It's less than half, less than 50%, because a lot of extra processing power is needed for those mutexes and for those kernel threads that formerly were handled straight inline interrupt mode interrupt service routines, but now are spawned off into other kinds of more complicated Linux or computing kinds of process mechanisms like mutexes and so on and so forth. But this is a simple example that doesn't always apply, but I think that if you look around the industry and the literature, you'll find that it quite often does apply in many characteristics, in many kinds of systems. You're trading off better real-time performance for throughput. Other characteristics. It's an all Linux solution. That's the good part about it. All Linux APIs and programming paradigms are the same. And why do I even say this? It should be obvious. Well, we'll talk about some of the other solutions and how they might diverge from that a little bit. This includes all tools, but it does require, as I mentioned, driver modifications for virtually all drivers. It's compatible with core isolation and shielding techniques, where you're actually trying to isolate certain cores for certain operations, and this can actually help provide better throughput in a certain kind of bare metal, in certain kinds of environments where you're running the so-called bare metal model on other cores other than standard multi-core Linux. In other words, what that says is you're locking a single thread to a core and trying to shield it from all other Linux interference and applications. And that model works pretty well, but it doesn't work well if you actually require multi-threading in that model. Bare metal is orthogonal to multi-threading. It does, of course, it is completely compatible with SMP style load balancing if you don't use core isolation, for whatever that's worth. It's well known that actually Linux SMP does not do a very good job in very high throughput or real-time responsiveness environments. Look at all the different scheduling algorithm work that's being done here. In fact, usually it's the case that thread-based load balancing is a difficult problem to solve. It's a very difficult problem to solve, and it quite often doesn't scale to larger number of cores. So SMP-style load balancing works very well with compute-intensive applications, high-performance computing, but that's not what we're talking about here, is it? So, standard Linux memory protection, of course, it's standard Linux power management. So these are some of the nice features of the preempt RT characteristics. One other thing that I didn't mention here, but it's implied, is what I said before. You have to reinstall it every time you upgrade to a new kernel because it's modifying the kernel. So this presents a configuration management and sort of maintenance and build kind of issue for you, if that's an issue for you. So let's move on to LWRT, or lightweight threading model. And we're referring specifically to an ENIA implementation of an lightweight threading model. The ENIA lightweight threading model, lightweight runtime environment, depends on a vertical partitioning concept where we basically are using core shielding and core isolation to separate the system into a real-time domain and a non-real-time domain. I'll show you that in a second. And the idea is that the real-time domain wants to use Linux as little as possible, if at all. The real-time partition does not need or does not even want to use the full POSIX or Linux APIs. Why? Because those are often very heavyweight compared to other models, hence the term lightweight threading. POSIX threading, pthreads, and other models are very, very heavyweight if one really looks at it compared to other kinds of techniques like LWRT. So basically, the idea is to improve performance and real-time characteristics by partitioning the system into logical domains and avoiding the use of the Linux kernel and its resources as much as possible. So again, we configure processes and interrupts to run with core affinity, only minor modifications to the kernel to avoid running unnecessary kernel threads and timers and interrupts from timers and so on and so forth. On real-time cores. That's part of the whole core shielding, core isolation technique. And the idea is to try to avoid calling the kernel at all and instead use this lightweight or user mode execution runtime environment that we're talking about. I'll explain that more as we move along. The idea is that the use cases, we're targeting interrupt latencies at 3 to 10 microsecond average, which is slightly better than preempt RT can under common interrupt latency measurements and whatever. Although preempt RT comes close to that, we'll see that in a little bit later. And it's also applicable when the application requires multi-threading performance or multi-threading design, I should say, on the real-time domains. In other words, one thread, a la the bare metal model, bare metal meaning you're running one thread on a core, when your design cannot use a single thread but requires multi-threading. That's where the lightweight threading or LWRT environment comes into play. So how does LWRT work? Well, it partitions the system into one real-time domain and one non-real-time domain, as I said. As a user mode runtime environment, including a separate scheduler that runs entirely from user space. Okay, so that's actually the threading model or APIs that your real-time applications use. The idea is that you use that scheduler, the user mode scheduler, and don't go into the Linux kernel scheduler at all, which avoids a lot of context switch overhead and so on and so forth. Migrates some kernel functionality away from the real-time domain. That's the whole core isolation, core shielding kind of concept. And adds a specific kernel module to catch and forward interrupts to the user mode environment. In other words, handle the interrupts, the preamble of the interrupts, meaning access to hardware and hardware registers and dequeuing from descriptors or however the device works, or pulling it from accelerator queuing engines and whatever, and doing the rest of the processing in user mode space. Kind of like the preempt RT concept, really, where half of the interrupt handling is offloaded into Linux kernel threads. But in the lightweight LWRT environment, because the scheduler is so much faster, as we shall see, then handling interrupts, turning interrupts into lightweight threads as opposed to Linux kernel threads, gives you a real boost in performance. So what's the benefits of LWRT? It provides both low latency, meaning very good real-time deterministic response, and very high throughput. Provides a solution unencumbered by GPL considerations. So just to let everybody know, the LWRT environment is not a GPL licensed environment, so there's no concerns there about your application, because it is running all in user space. Right? Optimized APIs for real-time and exceptional low latency interrupt response time, all the way up to user mode. It's an all Linux solution, but the LWRT environment APIs are not quite Linux APIs. So Linux is running, and you have access to the full Linux kernel from the LWRT environment, but it doesn't use the same APIs. So I'm going to diverge now just for a few moments and show you some performance measures of LWRT versus preempt RT. And I'm going to go through this quickly, and we can talk about this later. First of all, scheduling latency. Remember, LWRT is a lightweight threading model. So what do you compare it to? You compare it to pthreads, the standard Linux pthreads. If you look at this slide, you see that LWRT has better than 10x lower scheduling latency than pthreads. So therefore, if your application, if your real-time application could benefit, I should say, from multi-threading, and it's designed that way, then you will save a lot of CPU cycles if you use the LWRT approach as opposed to standard pthreads. Message passing latency, in other words, passing messages from one core to another core. And remember, we're talking about a multi-core device here. So you've got the lightweight threading model running on some number of cores, and we've got preempt RT and Linux running on the other cores. And look at the wide dispersion in Linux in terms of message passing latency versus what LWRT provides. At its best, LWRT again is over 10x the performance in terms of message passing latency, meaning the time it takes the message to go from one core to another, than a standard Linux model. Interrupt latency. Now we're a little closer here, but you see there's a wider dispersion of Linux interrupt latencies compared to LWRT, but it does get down into the region that you sort of want in a lot of firm real-time systems, at least 10 microsecond interrupt latency response for Linux as opposed to LWRT. But LWRT is still slightly better than Linux interrupt latency. Let's talk about throughput and how one measures throughput. We did something sort of interesting here in terms of measuring throughput. We decided that the measure of throughput was a measure of idle time within a certain time frame. And a good way to sort of view this is to look at a multi-threaded application for LTE base station design, where you have 2,000 microseconds to process an LTE frame, and within that frame, the idea is to process as many cells as you can. Well, instead of saturating the network, whatever, we just measured, we said how much processing time is it going to take to get up to cell N, and we ran this benchmark with different levels of N. And then, once we're done with processing all cells in a cell, 1 or cell 0 to cell N, then the idle time left is available for processing more cells. So you get the idea here that the idle time then is a measurement of how much more processing throughput you can package it can pack in to this kind of frame. So it's a rather nice direct measurement of what one could call real throughput. When you start talking about packets and other kinds of things, it gets a little confusing because there's so much involved in processing packets and so on and so forth. And you can, this is actually a more accurate measurement, we believe, of trying to compute a real throughput-based measurement that is really apples-to-apples comparison between different processing models. So, here's the results. LWRT, markedly better throughput numbers, up to over 50% better, more than 50% better throughput numbers compared to Linux. So, in effect, LWRT is superior in Linux and preempt RT in almost all aspects of measurement of both throughput and real-time responsiveness. However, there are some issues. There's always issues when you or issues. So, what are some other LWRT characteristics? It's not an all-Linux solution because the lightweight threading model is a different API model and a slightly different programming paradigm. But it does include all Linux tools except those for thread awareness, those that depend on thread awareness. But it doesn't require any Linux driver modification. It uses all standard Linux drivers. So that's nice. So you don't have to upgrade LWRT or change it when you upgrade to a newer version of Linux. It's got, as I said, slightly better real-time response determinism than preempt RT, and the interrupt handling model is a lot cleaner. And it's much better than preempt RT for throughput, and even standard Linux for that matter. But it really works best if multi-threading in your application is necessary. It's part of the design when you can take advantage of this lightweight threading model. If you're not taking advantage of the lightweight threading model, then it just gives you maybe slightly better interrupt handling, but if it's a bare metal model, then they're both pretty much equivalent to, the LWRT model is equivalent to the standard Linux bare metal model. It doesn't support load balancing because the sort of vertical partitioning concept prohibits it. Well, I shouldn't say prohibits it. It would require very active, proactive load balancing where there was some meta scheduler around that could automatically load balance all of these threads and whatever across the cores, but that sort of destroys the vertical partitioning concept in itself. So that's, if load balancing is an issue, then there could be an issue with LWRT. So far, we don't have any memory protection between threading environments on a core. And and the best implementation then requires one pthread per core. So again, it's sort of related to the load balancing issue, not quite the standard Linux power management issue, although that can be worked on, because LWRT is a work in progress, so it's not quite there yet in terms of all we can do with it, but it is getting there. And now it's time for our next polling question.
Yes, thank you, Michael. This is our second and last polling question, and again, please choose one of the options on your screen and hit submit answer. Don't chat back your answer. The question is real-time latency or throughput most important to you? And the options are real-time latency, throughput, both, neither that much. So please choose one of those, hit submit answer. And once we have a good representation of our group today, which is rather large, we'll push out those results. And we seem to be building pretty well. Okay, I think I'm going to push out these latest results for you, Michael. There you go. Interesting. Okay, very good. Real-time latency actually is important to about 70% of the audience here, which is precisely the kind of audience we were hoping to attract. Somewhat interesting that throughput is, well, let's see, throughput got 60%. Throughput is a little bit less of a concern than real-time latency. And that tells me that the audience is more about more traditional embedded kinds of environments than they are about, sort of Linux server high throughput processing environments, some examples of which I mentioned. So I think this shows that our audience here is really targeting, is really focused on more traditional embedded, which has always been concerned with real-time latency, real-time determinism issues. So a very interesting result. Now, next topic, Open Event Machine. It's actually an open source project, and you can go on to sourceforge.net and look it up. I'm going to provide a brief summary of what Open Event Machine looks like. It partitions the system into one real-time domain and one non-real-time domain, very much like LWRT. It provides a run-to-completion model for individual contextless work packages. There is no threading or OS model. Even though Linux is technically running under it, the idea is that nothing in Linux is being used, not even interrupt handling. So in effect, the Linux kernel is virtually non-existent in this model if you wish to use it to its maximum effect. And I'll just briefly touch on what that means later. It doesn't require any Linux kernel mods, but it can use core shielding because it's you want to move, part of the deal is moving all Linux, non-essential Linux processes or Linux processes and interrupts away from the EM cores. The idea in the event machine model is not to have interrupts delivering events or data into the thing. It's more of a polling sort of scheduling model which takes advantage of hardware acceleration engines. So it doesn't need a special interrupt handling model. It needs a scheduler for events, for hardware interrupt events in either software in Linux or in hardware. Let's look at this a little bit more in detail. Event machine is primarily for data plane processing. And the model is that instead of running threads on cores, you have the concept of what's called events. And events are data, are data items, or hardware, data items from hardware, data from other software-generated applications, messages, or whatever, and each data item is associated with an object, an event object, which is a
application that has no threading model in it. It starts, it runs to completion, and it stops. And when it stops, then you can process the next event. Okay? So each event is data that's also associated with some piece of code, which is called the event object, or the execution object, EO. It's got several different kinds of OS primitives. It can work within an RTOS environment, but it works best in a non-OS environment. And I'll explain that in just a minute. It's a framework for distribution and scheduling in a multi-core scenario and has excellent scalability behavior and excellent load balancing behavior. Again, you can read a lot more on the open source environment, but I just wanted to summarize here. There's two kinds of models in Event Machine, a pull model and a push model. A pull model says that the cores, and there's two components here, a scheduler and a dispatcher. The dispatcher is the thing that actually schedules and calls the execution objects, the EOs, by dequeuing via the scheduler an event that shows up on multiple kinds of queues. And you can have multiple different kinds of queues with different kinds of scheduling behavior and so on and so forth. But each core is basically pulling from available events when a new event processes it, in other words, runs it fully to completion. When it completes, then it pulls the next event and so on. So you see, it's a very highly efficient kind of polling kind of algorithm or model. And load balancing is passive in this sense, but it's passive load balancing means you don't have to have a complicated algorithm to distribute applications to different cores. All cores are going to be as active or as loaded as they possibly can be by pulling available events out. So it's a natural load balancing mechanism. You can't have cache issues with certain kinds of queuing models that that Event Machine does. Multiple input, multiple output queues, single input, multiple output kinds of queues, and you can read up more about those later, but it's just an observation that we found. Push model is where cache can be improved because you're actually pushing, the scheduler is pushing events out to specific cores. So it's an active load balancing model where you do need to have some knowledge of which cores are available and what execution objects, which is the software that's actually processing the events, are running. And but it can be very effectively used with intelligent hardware and intelligent hardware queues. In fact, a lot of the scheduling algorithm can actually be implemented in hardware in many of your more modern systems on chip, and so on and so forth. In the OS Event Machine scheduling model, you can actually have an OS, even Linux, running underneath where you can have preemption and background jobs where you're actually saying, I'm going to run the Event Machine completely in scheduler IO mode, but if something, an interrupt, if you're using interrupts, happens, then I can preempt the Event Machine and run an interrupt, and I can run background jobs whenever there's something to be scheduled. So you can mix the OS and Event Machine scheduling model, but if you want maximum throughput, then you probably want to stick to an Event Machine, a pure Event Machine scheduling model. But again, I just am noting that you can mix the two if you wish, but you have to be careful about the impact of this operating system now running in conjunction with the Event Machine. Other Event Machine characteristics, not an all Linux solution. It's actually different APIs and programming paradigm on all the Event Machine cores, and this means tools as well, and it requires restructuring of code. It depends on core isolation and shielding, because you're basically saying you don't want Linux to be running on those cores, unless in the previous example that I showed you, you want it to be running, but then you're seriously impacting, or could be seriously impacting, its actual benefits. And what's the main benefit? Throughput. It's one of the very best models for maximum throughput on the data plane because it offers one of the best algorithms or possibilities for true load balancing and maximum utilization and optimization of all of the event machine cores. And real-time response is not really part of the equation. It's not really about, it's not part of any of the model. It doesn't consider real-time response. It's really just about processing events. It could result in really good real-time response depending on certain use cases. But in general, it just sort of ignores real-time response and just processes events queued up either by hardware or software as fast as possible in a scalable manner in a multi-core device. So it really is the best load balancing solution on the data plane that's available right now. But there's no memory protection on EM instances on cores to implement that between cores, or the EM instances on cores, because again, that's a heavyweight OS kind of concept. And you have to really have trusted applications in order to run this, a lot like LWRT. And not standard Linux power management here, but it's not a hard problem to solve in the pull model. Lastly, and we're coming to the conclusion, virtualization techniques. What does a real-time virtualization solution look like? The kind that I'm talking about. The kind that we're talking about here are what's called type 2 hypervisors, where you're virtualizing Linux on some number of cores, but you're reserving some of the other cores for real-time, what's called, again, the real-time partition or real-time applications, where those applications are not actually using Linux at all. Now, they may have Linux-like or POSIX-like APIs, but they're not actually running Linux. It's underneath underneath it all is some kind of real-time OS-like thin real-time OS-like entity. And you can see this kind of thing in various type 2 hypervisors, like a NIA hypervisor, implementations like ZenMI, RT Linux, and there's several others. It doesn't completely utilize the Linux ecosystem because part of the domain is really in essence a non-real-time domain, but you get classic real-time performance behavior, and this means it's suitable for hard and firm real-time applications in the real-time domain, but it's not an all Linux solution, as I just said. So, and this includes tools as well. And again, superior real-time response, excellent throughput, and you do have memory protection across cores via the sort of the kernel layer and the virtualization layer for Linux. The problem is that for hypervisors or these kinds of solutions, the best use case is really for legacy migration of previous applications where you want to migrate to Linux, or you want consolidation of Linux plus existing maybe real-time kinds of processors and whatever. So there's really a special use case, and it has to do with just individual customer needs and primarily legacy. Where are they trying to do when moving up to new multi-core processors? The reason that hypervisors are not more widely utilized, or these kinds of hypervisors are not more widely utilized, is because increasingly the community, the Linux community, is wanting to an all Linux solution, or a mostly all Linux solution. They really don't want, in this kind of solution, Linux is just virtualized above some other kind of entity. So it's multiple sort of vendor kind of approach here. And more so than some of the other implementations we've discussed, the lightweight threading model and the event machine, because those are relatively self-contained in user space. This is the thing this involves another entity that's actually running the multi-core device. So we're seeing, and this is just Ania's observation, that we're seeing less and less talk about virtualization techniques in embedded unless we're talking about these sort of legacy migration or consolidation of multiple OS systems into a single multi-core device. So, coming to the conclusion, the 4 ways for better performance in Linux. We spoke about the pros and cons of the Preempt RT patch set, good real-time responsiveness, suspect throughput, thin kernel or virtualization, good real-time response, good throughput, but really completely, you're running 2 OSs in the system. Vertical partitioning with lightweight threading, much less impact on the much smaller scale kind of implementation for Linux. It is still more of a Linux solution than the virtualization techniques, and provides a very superior lightweight threading model, but has a slightly different API for those user applications, and for some environments that can be an issue. But we're working on that, and we could potentially provide POSIX APIs in that environment if necessary. And then the event machine, which is superior throughput, not clear what its real-time responsiveness characteristics are because it's not part of the model, and so on. Ania supports Preempt RT in its Linux distribution. We have virtualization, a thin kernel kind of virtualization called Ania Hypervisor. We have Ania LWRT, and we're doing some research on event machine with Linux. So that concludes the presentation for today. I hope you learned something about several of these interesting and some of which cutting-edge techniques for really ramping up the performance, meaning real-time responsiveness and throughput in your embedded systems. And now I guess we can turn it over for a few questions.
That's right, Michael. We have a few questions. We have a few minutes. First question, does LWRT support dedicated multiple cores to real-time?
Dedicating multiple cores to, yes, it does, yes. You can LWRT, you can allocate any number of cores in a multi-core device to the real-time partition that run the LWRT user mode scheduler and runtime environment.
Okay, great. Another question, can you use LWRT and Preempt RT together, and does Ania support Preempt RT?
Yes, I think I just mentioned we do support Preempt RT in our Linux distribution, and yes, actually you can use LWRT and Preempt RT together. But the only impact, what that will do, if you do that, is you will get better real-time performance, interrupts latency performance on the Linux partition in the LWRT model with Preempt RT, and it will slightly but not much affect the real-time environment, because we have our own kernel module that handles interrupts, and that kernel module does not need to be impacted by Preempt RT, because we won't modify that for Preempt RT to take advantage of what Linux is doing there. So you can actually run the two of them together. That's a good question.
Okay, great. Another question we have here is, you said research for event machine on Linux. Are you implying that you have another implementation, an implementation of event machine?
Well, yes, good question. We actually have an implementation of event machine with our DSP operating system for DSPs, where we've actually done the merger of an event machine concept into a real-time scheduler, which we call Ania OSCCK. But that's a very specialized implementation for DSPs, and what we haven't done is done an implementation on Linux itself, which is A, the primary topic of conversation here today, and B, the area of most interest for implementation of event machines. OSCCK has its user base, and its legacy, its customer base, and whatever, but moving forward, Event Machine is more about integrating into a Linux environment. So, yeah, the answer is yes, and we have some good experience with Event Machine. So if you're interested, please don't hesitate to contact us. The possibility of moving forward with that model under Linux.
Okay, I think we have time for at least one more question. What mechanisms do you use for IPC between WLRT cores?
Well, that's another good question. Right now, we have a technology called ENIA Links, which is an open source IPC, message passing based IPC, transparent distributed model for communicating between applications on any device, on any core, intra-core, even outside the device, because it's fully transparent and distributed. So that's called ENIA Links. You can look it up. You can find out about it on our website. You can also go to SourceForge, sourceforge.net, and look up links because it's an open source project there, the Linux distribution of it. And that's the model we use. And it's a very powerful model, as you will be able to tell once you start reading about links. There's only one problem, though. It is a little heavyweight for core-to-core communications in multi-core devices. So one of the next things we're working on in the LWRT model is a more internal backplane pipeline IPC mechanism that doesn't use sort of protocol stack-like features that Links does. So we have ENIA Links right now. You can look it up, like I said, on our website or on SourceForge, and we're working on more advanced techniques, but I can't really, I'm not at liberty to discuss those at this point.
Okay, I have another question here, one last question, just a little bit of time. I'm not sure I understood the LWRT architecture concerning its implementation over a pthread. Can you explain again?
Well, yeah, the ideal model for an LWRT environment is to entirely use the lightweight threading scheduler, meaning I can put multiple lightweight threads on a single core and just use the user space scheduler. Now, in Linux, to even launch that environment, everything in Linux, pthread is basically the container for launching a thread. In other words, the scheduler, the lightweight scheduler, is the pthread, is the execution engine that is running the pthread. So the ideal model, if you want best performance, is a single pthread where you never try to invoke another pthread on the same core, because if you do, that goes down into the Linux kernel scheduler to schedule that other pthread, and as soon as you do that, if you recall the scheduling latency issues or comparison, now you're really interfering with the real-time capability, the best real-time capability or performance that you can get from LWRT. So but you're not prohibited from using multiple pthreads on a core, but the more you do that, the less performance you're going to get out of an LWRT model. So if you just use one pthread to launch the LWRT environment and your application only uses lightweight threading and not pthread calls, then you will get very excellent real-time scheduling behavior.
Okay, thank you very much, Michael, for explaining that so quickly. Ladies and gentlemen, we are now out of time. As I indicated earlier, this session will be archived in about 24 hours on www.spectrum.ieee.org/webinar. Once the archived webinar is available, A notification email will be sent to all the registrants. I'd like to thank our presenter today for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session. We hope you found today's event valuable and will return for future IEEE Spectrum webcasts.